Good morning, everyone. Okay, so I have the anxiety, perhaps the unfounded anxiety, that, my last demonstration, the method by which I demonstrated it was a little bit too cool and possibly distracted from what I was demonstrating. So I'm gonna try again here. I built a new model. This is a hexagon. Follow my fingers. It's got 90 degrees here. It's got presumably octagonal angles there. So I think like 135, if I remember correctly. And then another 90-degree angle there. So that's 1, 2, 3, 4, 5, 6, and then back to where we started. Number of angles, let me just verify this because I am half asleep. 1, 2, 3, 4, 5, 6. So, we're good. Alright, now here's the cool part. This hexagon becomes a square when it is either, let's keep the dots lined up, parallel or perpendicular. And this hexagon always has the two 90-degree angles. However, the other angles do start to change in relation to that side length there, which, when the dots are lined up, and when everything's perfectly straight, is the same as that side length there. So, that's my model. It converts angle into something that is dependent on straight lines rather than being something that is dependent on circles. And that's why I'm working on this, because circles are great, but I have a beef with them for just no particular reason. I mean, they're not evil. I mean, I like wheels. I like Sonic the Hedgehog, and he's spherical physics, but there you go, man. It's a 45-degree slice of the entire pie. However, if you get 8 of these, then you can make the entire pie from scratch. So let's focus on this corner here. I'll be right back. This corner here. Let me see. No, it doesn't really matter. Okay. Then we've got our 45 degrees. And then everything between here and here is fair game. And then, if we're using point and slope, which is, I mean, fine, like an x and a y coordinate, then, like, it's just slope. But then we flip them to get to this other side here. And the coolest thing ever is that, let me see if I can get a formula up in front of you guys. No equation yet, still working on it. One moment, I can't find it in my notes, so I'll just make it from scratch. Also, I'll show you my notes in a moment, they're kind of fun. One moment, almost ready. Okay, so I could be wrong here, because I just woke up with lots of energy, I'm not too focused. This is the equation I got wrong the other day, because I used -1 instead of -2, and that threw everything off, but that's what I got wrong yesterday. So anyways, we're gonna go on to, this nonsense. Basically, what I'm trying to do here, because this might not be fully accurate, is, you know what slope is. You take an x-coordinate and a y-coordinate, and it, or, like, a rise and a run, and it sends you to a place, and then you just connect that back to the origin. Well, you also know that, 1/1, its distance from the origin is the square root of 2, because that's just the diagonal of a square. So what I'm saying here is, and actually, just realized I goofed up. Okay. So for the rest of this equation, flip x and y because I was a dork. So you take y by the square root of 2 because the higher something goes, the closer it goes to being the square root of 2. And our Sonic the Hedgehog is invariant, and my head just likes to work in reverse, so this is positive x for the purpose of what my hand is doing here. Okay, so you take that, and you multiply each one separately by this, so x multiplied by 1, that's just going to be x. Square, but in alternate realities, it might not be 1, so that's why we're just doing the form of the equation this way. And then in y, you do it times square root of 2, which is going to be some bigger number than y. So then what you get here is x1 is z, and y square root 2 is d. And you take d and z and you add them together, and that gets you some random number, and then you divide it by x and y added together. And what I'm trying to do here, because I'm kind of dumb because I just woke up, is you're going to have a list of numbers, basically. That's what multiplication is. It just compresses the list. So take the number of numbers by the types of numbers you added up to get the average, like how many times the square root of 2 is appearing there times how many times 1 is appearing there, or reverse that because I'm not paying attention. And then this is your number of times, and these are your numbers. So you divide them together, and it gets you W. And then you take the W, and you go back to your original X and Y, and remember to flip these, and you multiply each by W, and W is going to be some smaller than 1 number, and that modifies the values so that you wind up with fixed distance. So now, no matter how close you are to being the diagonal of a square, you're going to get that appropriate amount of the square root of 2 removed from you. The closer you get to being 1, the less of an issue that becomes. So what we have to do is figure out, like, how close we are to the square root of 2 as a discrete value, and how close we are to being 1, and then subtract that amount of or do nothing to that amount of 1 and subtract that amount of the square root of 2 from you in order to make sure that no matter where your point actually is, it's as if it's on a circle. But that's only true for a 45-degree slice. And that's what I was talking about yesterday, albeit less literately. So what I'm trying to say here is that if you've got a 45-degree slice of a circle, and you know exactly what you need to do, because reflections are simple things, to move that around to create 8 different slices of a circle, then you've got an entire circle. And with that entire circle, you can then just use basic translation equations to move it around to wherever you need it to be and scale it to whatever size you need it to be. So this is how to draw a circle without pi. And that's what I was excited about the other day. That's all. I'm not mad at anybody here. I'm awkward as heck. All of that. So, rock on, y'all.